Welcome back, ladies and gentlemen. It's Miss Flanagan here. Today we're talking about kinetics and equilibrium. First, let's start with kinetics. In kinetics, we talked about the collision theory, which essentially explains how particles collide and react with one another. A reaction is most likely to occur if reactant particles collide with the proper energy and orientation to make an effective collision. That's the key with collision theory, an effective collision. Think about when you hit a baseball. Sometimes you foul tip it, sometimes it hits off the back net, and sometimes it's a home run. Like this example here. That is the perfect energy and orientation for an effective collision to occur. There are 5 different factors that increase the rate of reaction. First is increased temperature. It increases the number of effective collisions. 2, increased concentration. The more particles there are, the more collisions there will be. 3, increased surface area. The more space for particles to collide with one another. 4, adding a catalyst. It speeds up the rate of reaction by lowering the activation energy. And 5, the nature of reactants. Ionic reactants react much faster than covalents do. Next, in kinetics, we talked about the potential energy diagram curves. They look like a roller coaster. Arrow 1 starts at this bottom line and goes to this first flat part. That's the potential energy of the reactants of the forward reaction. If we come over here, it's not drawn in, but if I started here from this horizontal line at the bottom and went up to this horizontal line, this small arrow here would be the potential energy of the products of the forward reaction. Next, arrow 2, all the way from the bottom to all the way to the top of the hill, that's your activated complex. At this top part, that's exactly the moment where bonds are breaking and bonds are forming and the actual reaction is happening. Arrow 3 is the activation energy of the forward reaction. Even though it's drawn over here, if we just slide it over, it would match up to this piece right here. And think, if you're sitting in your roller coaster right here, all that energy you need to get to the top of that hill is the activation energy. And then, once you reach here, it's smooth sailing to the bottom. Then, arrow 4 is this arrow here. It's the difference between the products and the reactants. Remember, pepper. Potential energy of products minus the potential energy of the reactants is pepper. Also known as delta H, aka heat of reaction, or enthalpy. Delta H can be negative, resulting in an exothermic reaction, or positive, showing an endothermic reaction. In exothermic reactions, like picture B here, the products have less energy than the reactants, so the delta H is negative, and the energy is released. So energy is written on the products or the right-hand side of the reaction. Endothermic, like the picture on the left, is absorbing heat, so energy is written on the reactant side or the left-hand side of a chemical reaction, and the products have more energy than the reactants. Notice that the product line is higher than the reactant line in an endothermic curve. Kind of looks like a duck. Beak, nose, endothermic, has a D in it. And then exothermic, the reactants line is higher than the products line. Just a fun way to remember it. Next, in kinetics, we use table I. It has all different delta H values. Remember, a negative delta H means it's an exothermic reaction. And we use the coefficients to explain how many moles of a certain chemical will release or absorb a certain amount of energy, according to table I. Next, we talked about entropy, which is a measure of disorder or randomness. Gases are the most disordered. Solids are the least disordered. Entropy increases as you go from solid to liquid to aqueous to gas. Solids having the least entropy, gases having the most. And finally, for kinetics, systems in nature tend to undergo changes towards lower energy, making them more stable, but higher entropy, meaning more disorder or randomness. Now, for equilibrium. In equilibrium, the rate of the forward and the reverse reaction are equal. Remember, RECC, rec. And the concentrations are constant. Again, the rate of the forward and the reverse reaction are equal, hence the E, and the concentrations are constant. A saturated solution is at equilibrium because the rate of dissolving equals the rate of precipitation. Often they will use a curve similar to the one you see here. At this point, where the red arrow is pointing, equilibrium has been reached because now the rates are equal. And lastly, in this unit we talked about Le Chatelier's, and Le Chatelier's principle focused on temperature, concentration, and pressure. He said that if you increase the temperature or concentration, the equilibrium will shift away from the side that you added it to get rid of it, to balance out that equilibrium again. Conversely, if you decrease the temperature or you decrease the concentration, there will be a shift in equilibrium towards that side to make it back. Pressure is a little different. Pressure only affects gases, and so an increase in pressure means a decrease in volume, and so it shifts to the side with less moles. Conversely, a decrease in pressure, again only affecting gases, shifts to the side with more moles of gas because the volume has increased. And remember the saying, add away, take towards. When you add something to one side, it's going to shift away from that side you added it to reestablish the equilibrium. And conversely, if you take something away from one side, it's going to shift towards that side to replace it. That's all for now. Happy studying!